Hello and welcome to the last video of topic 8. In this video we're going to look at another type of integral we can tackle using our methods developed so far, namely integrals of real functions multiplied by complex exponentials. These are particularly common when looking at Fourier transforms that pop up all over the place in physics. First, as a quick recap of what we saw in the previous video, we looked at computing real integrals with infinite limits. And we also saw that the condition for the contribution on an arc of a semicircular contour, a condition for that to vanish, is that the function decreases more strongly than 1 over z in the large z limit. The intended learning outcomes for this video are that you should be able to compute integrals of real functions multiplied by complex exponentials, and you should also be able to apply something called Jordan's lemma to show that contributions on an arc vanish if the real function in the integrand vanishes in the large z limit. As always, you'll have lots of chances to test your understanding using the problem sheet. This sheet is quite long and has examples of all the types of integrals that we've covered in this topic. I want to emphasize that I hope you enjoy applying the methods from this topic. It's really very satisfying seeing them at work. And with that, let's begin this last video of topic 8.
In this video, we're going to be looking at integrals with complex exponentials. And again, we'll see that our tools from complex analysis will help us. The type of integral we're going to be looking at here looks something like the integral from minus infinity to infinity, some real function times a complex exponential e to the I ax dx. We're going to say that a is a real number and it's greater than 0. You might recognize that this is a Fourier transform. As in the previous video, we're going to make a couple of assumptions about our function. In the following, we're going to assume, first of all, that the analytic continuation, f of z, is analytic in the upper half plane except for a finite number of poles. That's the same assumption that we made last time. The second assumption we're going to make is that the limit, as the absolute value of z tends to infinity, of our function is 0. And that's true for when the argument of z is constrained to lie between 0 and pi. You'll note that compared to the assumptions in the previous video, this is a less restrictive condition than imposed earlier. Earlier we had that our function had to decrease more strongly than 1 over z. Here we simply need the function to approach 0 as the absolute value of z tends to infinity. We're going to be interested in a contour integral, and as before we're going to use a semicircular contour. We can again employ the semicircular contour. Draw a picture. We have this contribution here that sits on the real axis, but for convenience I've drawn it as slightly shifted up, just for clarity. But this blue line does indeed lie on the real axis. And then we have the semicircle. we're going to call this bit C1 and this bit C2. Let's look at our contour integral, the integral along this semicircular contour C of f of z e to the I a z dz. I should also label minus r and r on the real axis. As before, you'll note that on the section of the contour C1, z is the real number x, and so taking the limit as r tends to infinity of the integral along C1 is going to return our desired integral, I. What about on the arc C2? Here, as before, we're going to have z is r e to the I theta, and so we can write that the integral along C2 which for convenience I'm going to call I subscript C2. This is the integral from 0 to pi of f of r e to the I theta, and then we've got e to the I a z, and we can write this as e to the I a, and then z is given by r cos theta plus I r sine theta, and differential becomes I r e to the I theta d theta. Next, let's look at the magnitude of this term. This is the magnitude of the integral f of r e to the I theta, and then we have e to the I a r cos theta, and then e to the minus a r sine theta times I r e to the I theta d theta. Quickly looking back at our second assumption, we assumed that our function f of z was going to tend to 0 as the absolute value of z tends to infinity. So let's think about what happens to this term IC2 as r tends to infinity. We can say that taking r to be sufficiently large, we can say that the absolute value of our function on the arc, that's going to be bounded from above by epsilon, which is some small number that's going to tend to 0 as r tends to infinity. I'll note here that this is 4 theta constrained between 0 and pi. Okay, then our second assumption tells us that as r tends to infinity, this bound is going to tend to 0 and our function vanishes. Returning to the absolute value of IC2, this is now upper bounded by epsilon, which we can take out of the front, and we can also take r out of the front. We're left with the integral from 0 to pi of, and then the e to the I a r cos theta has unit modulus, and we can also ignore the I e to the I theta on the right hand side, and the remaining terms give us e to the minus a r sine theta d theta. Next, we're going to notice that the integrand is symmetric. About theta equals pi by 2. That's a standard property of the sine function. That allows us to rewrite this instead as an integral from 0 to pi by 2 of e to the minus ar sine theta d theta. How do we tackle this integral? Well, let's look at what the sine function looks like in this integration range. Let's look at sine theta in the range 0 to pi by 2. I'll draw a picture. This is theta. This is sine of theta. We know that its maximum is 1, and that occurs at pi by 2. And out here is pi. And I can draw this. That's not particularly symmetric, but you get the idea, and I'll label it to make sure it's obvious that this is sine theta. And actually I'll remove this label here. Now I'm going to draw a straight line. And this straight line is described by 2 over pi times theta. What's the significance of this? Well, in the integration range, that's theta running from 0 to pi by 2, you can see that 2 over pi times theta is always less than or equal to sine of theta. That means that in our expression above for the absolute value of C2, we can put an upper bound by replacing the term in the exponential as follows. This is now less than or equal to 2 epsilon r, the integral from 0 to pi by 2 of e to the minus a r times 2 over pi times theta d theta. You can perform this integral explicitly, and you'll find that this gives 2 epsilon r and then 1 minus e to the minus ar over 2ar over pi. Rewriting this, we have pi over a times epsilon times 1 minus e to the minus ar. Finally, we can consider the limit as r tends to infinity of the absolute value of this contribution, and that's going to be the limit as r tends to infinity of pi over a times epsilon, and we know that epsilon tends to 0. Therefore, this contribution along C2 vanishes. This result, where we've replaced the sine of theta appearing in the exponent with 2 over pi times theta, in order to show that this contribution along the arc vanishes as r tends to infinity, this result is called Jordan's lemma. I'm going to make a final point here related to Jordan's lemma. Note it was important here that we used a contour in the upper half plane. And why is that the case? Well, it's because we took the real number a to be greater than 0, and that means that the exponent minus a r sine theta is negative throughout the integration range, and therefore, as we saw, yields a negligible result. In the contribution C2. On the other hand, if we had considered things in the lower half plane, this exponent would be positive, and that means that the integral would diverge. So in this case, where a was greater than 0, we had to take the contour lying in the upper half plane. However, a contour in the lower half plane would be suitable if the parameter a, the real parameter a, was actually less than 0. To recap what we found here, we have that the contour integral along that semicircular contour C in the upper half plane of f of z e to the I a z, well, that was just the same as the integral from minus infinity to infinity of the real function times the complex exponential. And as usual, we can evaluate the complex integral using the residue theorem. So this would be summing all of the residues of our function at the poles zk. And the requirement was that our function tend to 0 as r tends to infinity. And this is our result for integrals with complex exponentials. Let's end this video by looking at an example. Let's consider the integral between 0 and infinity of cos of x over x squared plus 1 dx. First of all, we can simplify this into exponentials in the following way. We know that we can rewrite cos x as a half e to the ix plus e to the minus ix. And that means that our integral becomes a half, then the integral from 0 to infinity of e to the ix over x squared plus 1 and the second term, a half, the integral from 0 to infinity of e to the minus ix over x squared plus 1 dx. you'll note that the second integral has an odd integrand. The second integrand is odd. That means that f of minus x is minus f of x, and that means we can write this as this first term doesn't change, but this second term picks up a minus sign, and we can flip the integration limits to give us this. We've got the same integrand on both sides, so we've managed to write the integral of cos of x over x squared plus 1 as the integral from minus infinity to infinity of e to the I x over x squared plus 1 dx. And you'll notice that this is of the form that we care about. As usual, let's analytically continue our real function to a complex function. Here f of z is going to be 1 over z squared plus 1. And you'll immediately note that this does indeed tend to 0 as the magnitude of z tends to infinity. So the contribution along C2 will vanish, and the parameter in the exponent a is plus 1 for e to the I ax. That tells us that we should use a semicircular contour in the upper half plane. We can rewrite our function as 1 over z plus I, z minus I. This has simple poles at z is plus or minus I. Let's draw a quick picture. We have our semicircle. This contribution gives the integral we want. This contribution vanishes, and the only pole that we enclose is the one at plus I. And as usual, we've taken r to infinity. Okay, so to evaluate this contour integral, we're going to need the residue at this pole. The residue of f of z e to the I z at plus I. Well, we're going to use our result from the end of topic 7. This is the limit as z tends to I of z minus I, and then times the integrand, which is e to the I z over z plus I, z minus I. This gives us e to the I squared divided by 2i, which is 1 over 2ie. Hence we have that the contour integral of f of z e to the I z dz, we know that this gives us the integral from minus infinity to infinity of e to the I x over x squared plus 1 dx. This is 2 times the real integral that we want to calculate, and by the residue theorem this is 2 pi I times 1 over 2ie. And we're left with our final result that the real integral we set out to calculate is pi over 2e. That's the end of this third video of topic 8, and that's also the end of topic 8. As a recap for this topic, in the first video we saw how analytic continuation allows us to use all of our tools from complex analysis, such as the residue theorem, to approach real integrals, and we put down a recipe for how to do this in general, where the substitution z equals e to the I theta allowed us to use the residue theorem to evaluate real trigonometric integrals. Next, we looked at infinite integrals, and we made two assumptions. Firstly, that our function f of z is analytic in the upper half plane, except for a finite number of poles, and we also assumed that in the large z limit, in the upper half plane, our function vanishes more strongly than 1 over z. With those assumptions, we then saw how a semicircular contour in the upper half plane, together with the residue theorem, allowed us to calculate infinite integrals. And in this last video, we've tackled integrals with complex exponentials. We made two assumptions again. The first was that our function is analytic in the upper half plane, except for a finite number of poles. And the second assumption was that in the large z limit, our function tended to 0. We presented Jordan's lemma to show how contributions along arcs vanish as r tends to infinity, and we finished with an example of calculating an integral with a complex exponential using the residue theorem. As always, you'll get plenty of practice of all of this in the associated problem sheet. That's the end of topic 8, and next up is topic 9. Thanks for listening.